Hello my friends. I'm Archimedes. Today I am gonna introduce you a very interesting work, Global K-Space Interpolation for Dynamic MRI Reconstruction using Masked Image Modeling by Jiaxin Pan and his friends at the Technical University of Munich. In magnetic resonance imaging, the final images are reconstructed from the MRI raw data, K-space. In cardiac MRI, to acquire a fully sampled MR image, usually a long scan time of up to 10 minutes is acquired, which can incur patient discomfort. Therefore, to speed up the scan process, accelerated MR is applied. Fewer K-space data are collected, resulting in undersampled K-space and corrupted MR images after Fourier transform. In this context, an inverse problem is to solve, and the MR reconstruction is required to restore the MR images. Conventional methods usually handle the MR reconstruction problem in image domain after the Fourier transform, for example using an image domain denoising prior. An extra DC term is usually applied to ensure the data consistency to the K-space. However, there are some limitations of image domain-based methods. First, the denoising prior is usually specified to a certain noise level of an undersampling rate. It lacks of the generalizability to other noise type at other undersampling rates. Further, it works on corrupted data in the image domain after the Fourier transform. The tissues of interest in image domain can already be distorted before the denoising kick in, making the restoration task more difficult. On the other hand, we can also reconstruct the MRI by interpolating the K-space before Fourier transform. In contrast to using denoising prior in image domain, K-space interpolation works on reliable data without data corruption. K-space-based methods have a consistent task of interpolating missing data, even though the undersampling factor may vary. This makes K-space interpolation methods robust and generic over multiple undersampling factors. There are also some limitations of current K-space interpolation methods. Some of them require calibration signals in K-space, restricting the flexibility of K-space sampling. Further, almost all current works use local operators to process K-space, overlooking the long-range dependencies of the frequency domain. Moreover, they do not learn the presentation of the sampled data, which contains meaningful patterns that are easier to process. Therefore, in this work, they propose global K-space interpolation for dynamic MRI reconstruction using masked image modeling, which enables high flexibility without using calibration signals, has a global dependency modeling, and can learn the rich representation of the sampled K-space data. To realize these goals, they apply masked autoencoders as their tool. It is a mask image modeling method which is a perfect matchup to their application. It has high flexibility with random masking image modeling, global self-attention maps to learn the global correlation, and can learn rich representation from limited data. They apply the undersampled K-space of the cardiac sequence as the input and interpolate it with their proposed method, termed as k-IRM. By the way, after grappa, raki, caipirinha, and sake, we have one more alcoholic beverage in MR reconstruction. They stack the 2D plus T cardiac MR sequence along the T dimension. They then feed the sampled data of the MR sequence to k-IRM, in which the rich representation of them is learned and the missing K-space points are interpolated. Further, they implement iterative refinement block to refine the K-space iteratively, in which every 2D plane is refined gradually. They also apply the high dynamic range loss to handle the large magnitude difference in K-space. Here are the reconstruction results of the proposed k-IRM compared to TV norm, L plus S and DCCNN at acceleration rates of 4 and 8. It is noteworthy that k-IRM and DCCNN are both trained only on R4 undersampled data. Different hyperparameters for TV norm and L plus S are demanded for R4 and R8 cases. These image domain-based methods demonstrate inferior reconstruction at R8 since there is a mismatch in artifact characteristics between R4 and R8. On the contrary, k-IRM shows superior robustness and generalizability because the task of interpolating K-space for R4 and R8 remains the same, estimating missing K-space data. What's next? They want to extend their current work from single coil setting to multicoils and to evaluate their method on prospectively collected data. Last but not least, one can use their work as a pre-training task since the image reconstruction itself can be regarded as an intermediate step. In the future, downstream tasks like cardiac segmentation and disease classification can be built upon it. So my friends, it's the time to say goodbye. If you are interested in their other work, please visit their lab at the Technical University of Munich and Imperial College London. I am Archimedes. See you next time.